got in the last couple of classes that we will need in today's class. Focusing at the moment just on Lorentzian space, which is where we actually working. Let us remind ourselves that we had the following equations. C was defined, this matrix C was defined so as to obey gamma alpha was equal to minus 1 to the power n, minus 1 to the power n gamma transpose. Gamma alpha transpose was equal to C inverse gamma alpha C. Okay. We had, this was one equation that will be useful. The second equation that will be useful is that C transpose was equal to minus 1 to the power n into n plus 1 by 2 C. And these two equations were true both Euclidean and Lorentz. And the reason for that was that the difference between Lorentzian space and Euclidean space was that we multiplied one of the C's with an I, but that didn't change any transposition properties. Okay? The equation that was sort of different in Lorentzian and Euclidean space was the following. We had C star was equal to in Lorentzian space was equal to minus 1 into n minus 1 divided by 2 times identity. This is Lorentz. We had n into n plus 1 by 2 times identity for Euclidean space. But Euclidean space will not play much of a role in what goes forward. Okay? And the second thing I wanted to remind you of was that we had this table. So we had SO 2n plus 1. And this guy was n is equal to 1 or n is equal to 1 was real. And what else was real? SO 2n plus 1, which is really SO 1 comma 2n. N is equal to 1 or 0 mod 4. Yeah, of course. N is equal to 1 or 0 mod 4. Everything was real. We had real spinors. Okay? N is equal to 2 or 3 mod 4. We had pseudo-real spinors. Okay? And for SO 1 to n minus 1, we had n is equal to SO2 should be real. So 1 and SO8, SO10, SO 1, right, exactly. So sorry, just 1 mod 4 was real and chiral. N is equal to 3 mod 4 was pseudo-real and of course chiral. And n is equal to 0 and 2 mod 4 was complex. You remember the rule for complex was opposite to what it was for Euclidean. If n was even in the Lorentzian algebra, the spinor algebra was complex. Whereas if n was odd in the spinor algebra for Euclidean case, the spinor algebra was complex. Okay? And Okay, excellent. And once again, to get a a reminder of this, in 3 dimensions or in 9 dimensions. Okay, so in 3 dimensions or in 9 dimensions, or actually also in one dimension. Quantum mechanics, the example we looked at right at the beginning of the class. 1 is same as 9, or in 3 dimensions we had real spinors. That we saw, right? Our first quantum mechanical example involved real spinors. Okay, and in 5 and 7 dimensions, we have only pseudo-real spinors. And then moving to even dimensions, in 2 dimensions or 10 dimensions, we have real chiral spinors. In 4 and in 4 and 4 and 8 dimensions, we have complex spinors. And in 6 dimensions, we have pseudo-real spinors. Okay? Fine. So, at the end of the last class, we had started working out, we had started writing down various supersymmetry algebras. So let's complete that in this class. Okay. So I think I started with d is equal to 1 with okay, d equals 1, 3 mod 8. D is the full space-time dimension. This is the case 0 or 1 here. Okay? Because 0 is 1, n equals 0 is d equals 1, and n equals 1 is d equals 3. So we're looking at quantum mechanics, or 3-dimensional quantum field theory, or 9-dimensional quantum field theory. Okay? And in that case, we wrote down a sort of guess algebra. And the algebra we wrote down was Q alpha, Q beta is equal to gamma alpha C. Okay, now we have to be a bit careful. This is mu. So this is P slash. P slash, so alpha, beta, gamma, alpha, beta. You remember that we had spinor conventions. That's the last thing I should remind you of. We had psi alpha, or gamma alpha beta, and C alpha beta. Okay? To know when spinors are up or down is very useful, because you can write covariant equations. And C is the object that can lower a spinor indices. C inverse is the object that can raise spinor indices. Okay? We had this. We put some, let's put some ij indices here. So we tried with the delta ij plus C times Zij. Okay. Now, I've written this suggested algebra down. You remember everything else in the algebra was trivial. What was important was whether the anti-commutation relations of Q with itself. Okay? Now, I've written this algebra down, but there are many things we need to check about it. Okay? So, the first thing we want to check is the following. The first thing we want to check is this term here is clearly the same as this term here is Q alpha I, Q beta j plus Q beta j alpha I. That's what it means. Okay? So clearly it's symmetric under simultaneous interchange of alpha beta and ij. Okay? So whatever the left-hand side has a property that under simultaneous interchange of alpha beta and ij, it remains invariant. Therefore, the right-hand side must have the same property. Okay? Now let's look at each term that appears on the right-hand side. So let's start with this guy. Okay? Delta ij is invariant under ij interchange. So the term that multiplies it must also be invariant under alpha beta interchange. But under alpha beta interchange, when you've got a product of matrices, is the same thing as taking transpose. Okay? So the way that this is going to be invariant is if gamma mu, the elements that appear here are gamma mu times c. Okay? And I take transpose of this. Okay? If I take gamma mu times c and I take transpose of it, that's interchanging alpha beta indices. So I want to know what that is in terms of the untransposed quantities. Is this clear? Okay?
There can be many symmetric matrices. Why you just took delta ij?
Why did I just take delta ij? Right. Why did I take delta ij? We did the same last time in quantum mechanics, firstly. Right? Okay. Now,
I mean, for example, delta ij you took, you said that it will be arbitrarily.
yeah. So why couldn't we have something more more general? Yeah, that's probably true, right? That's probably true. That's probably true that if you take an arbitrary constant symmetric matrix, that SO, in fact, we will see these SO, these Qs will transform under vectors. Okay, so let's suppose that Ij. Okay. Let's suppose that I is equal to 1 to, let's say, n. There's some number of i's. Okay. There will be an associated, in this case, SON symmetry group. Okay. And
Oh, you are saying you can say only one tensor to delta ij, and then the next is.
you see, basically the scale also of Q is up to us. So, as long as we get a matrix that up to these SO transformations becomes diagonal, then we can rescale our Qs, okay, to make them P's. There may be some issue involving plus minus signs, but I think you can probably always just do that. That's a good question. I'll think it through as we're talking and maybe give you a more complete answer. Okay, but let's come back to this guy. So this guy was equal to C transpose times gamma mu transpose. Okay, now what about C transpose? Okay, C transpose was C transpose here. C transpose was equal to minus 1 to the power. Okay, wait. First, now we've got C transpose times gamma mu transpose, and now we want to look at how I can rewrite that in terms of something without a C. Sorry, in terms of without a transpose and the reverse order. Yes. But then we'll also have to take C through.
Yeah, but gamma mu transpose is C inverse gamma mu.
That's what I'm going to do. Right. Yes, that's what I'm going to do. Yeah. Sorry, what was?
I have one clarification.
Yes.
Here, alpha means all the alpha is the group of all square radius.
What do you mean?
Alpha and beta.
No, these are just ordinary spinor index. Why tensor? Yeah. So this is one spinor index and this is another spinor. It's not more than one, if that was what the question was. Yeah. So I think Kanu was helping us do this algebra. So Kanu's comment was, I think, the following. We know that from that equation up there, we know that minus 1 to the power n gamma alpha transpose was equal to C inverse gamma alpha C. We know this. So Kanu, I think, wanted us to multiply C here. But we've got a C transpose here. So this is true, so but we can just multiply, but C transpose and C are related by this extra factor. So we have minus 1 to the power n times minus 1 to the power n into n plus 1 by 2 times C transpose gamma alpha transpose is equal to gamma alpha C. This is what you wanted, right? Okay. And now let us look. In the case that, let's take it in the two cases. Suppose n is equal to 0. So the two cases were 0, n is equal to 0 or 1. For n is equal to 0, both these are 0. So this is 1. For n is equal to 1, this is a minus sign, but this is also a minus sign. So the product of the minus signs is 1. And so we implies that C transpose gamma alpha transpose is equal to gamma alpha C. Okay? So the matrix that should have been its own transpose is its own transpose. Okay, so we have shown, therefore we have shown that implies P slash C alpha beta is equal to P slash C beta alpha as required. Okay, good. So one consistency check works. Okay, now what about the other one? What about this other term? Shuman was asking about this last time. Okay, what about this other term here? Okay, so the other term here, well, let's take its transpose. That just gives us the transpose of C. Okay, and the transpose of C was had this factor here. Okay, so in this case we get that C transpose is equal to C, n is equal to 0 mod 4, but is equal to minus C, n is equal to 1 mod 4. Okay, so for this algebra to make sense, this Zij here will have to be equal to symmetric n is equal to 0 mod 4 and is equal to anti-symmetric n is equal to 1 mod 4. Okay, let me check that this is what they get. So for 1 is symmetric and 3 is antisymmetric. Perfect. Okay. So as long as we put these properties on the Zij, this algebra at least passes the transposition test. Okay. Now you might ask, is there something else we want to check about this algebra? Okay. So another thing that you might want to check about this algebra, so I'll go to that board since we can keep all the formulas up here, maybe even bring some of this down. Another thing we might want to check about this algebra is the following. We might want to check, you see, what I did not tell you clearly enough, but let me say it now, is that in these dimensions, remember, we could have real spinors, and these Q's we're going to choose them to be real spinors. Okay? But this now requires a test, because real spinors obeyed an equation, right? Real spinors obeyed the equation Q alpha was equal to C gamma 0 Q star. That was the equation we decided to impose on real spinors. Okay? So this algebra is meant to be true for supercharges that obey this equation. Okay, but if that's the case, then I should be able to take the commutation relations we've written here, complex conjugate, okay, and then multiply by the right factors of C and gamma 0 and get back the same algebra. So what's the check? What do I have to check? So what I have to do is to take Q alpha I, Q beta j. Now suppose I take this and complex conjugate it. So that becomes Q star, Q star. Then I multiply by, the alpha index here. That's the first index in the matrix that we're writing on the left hand side, by C gamma 0. Okay, then I want to multiply the beta index by C gamma 0, but that is multiplied from the right, so I should transpose. Okay, and therefore I want to multiply by gamma 0 transpose C transpose. That object should just be equal to Q alpha I, Q beta j. This is the check. Right? Because after doing these multiplications, I've done nothing if Q actually obey this equation. Is this clear? This is what we have to check. Right. What does it mean when we say, when we want to write, we take some index, let's call it zeta, and I multiply with a matrix. What it means is zeta, let's say beta alpha, m beta alpha. This is what it means. Okay, but when we want this index to contract with this. But to do that we need to, if we're multiplying from the right, that's the same thing. So this is m zeta, but that is also zeta m transpose. Right? Because we want this in the second index to contract with this guy. To write it as matrix multiplication, we need to transpose. Is this clear? Right? It's the usual thing. If you've got an index from the right and you want to do matrix multiplication, that becomes a transpose. And then because if I had a transpose, I had to change the order as well. Because AB transpose is B transpose A transpose. Is this clear? Okay, excellent. So, now, so this gives us a check on the right hand side. So let's take the terms at the right hand side one by one. Delta ij is playing no role here, so I'm going to drop it. So I wanted gamma mu times C. Then I wanted to star it. Then I wanted to multiply by C gamma 0. And then I wanted to multiply by gamma 0 transpose C transpose. Okay? And if everything's working out right, this should be the same as gamma mu times C. Okay? Well, very good. So let's just proceed. Okay. So first thing we will do is use the transposition rule. So our transposition rule, just to have it again, was minus 1 to the power n times minus 1 to the power n times gamma transpose is equal to C inverse gamma C. Okay. So we had a gamma transpose here. So let's multiply this on this side with a C inverse. Okay, let's do that. Now, taking now C and C inverse, First, I'm going to make this is minus 1 to the power n gamma transpose times C inverse transpose is equal to C inverse gamma times that factor, which was minus 1 to the power n to n plus 1 by 2. Right? I've just added a transpose at the expense of adding this extra phase. Okay? Whether we took C, because C and C inverse were proportional to each other, whether we took C or C inverse through didn't matter. Okay? So, this object is the same as taking this guy through and make it. So, this is equal to minus 1 to the power n and taking this guy through. Sorry, what am I doing? Sorry, what am I doing? Why did I? Sorry, what was I doing here? I had this.
So you have proved that gamma mu C mu transpose is gamma mu C mu.
Gamma mu C mu transpose is gamma mu C mu. Oh, good point. This I proved, yes. So gamma mu C mu transpose is gamma mu C mu. Okay.
I mean C gamma, yes.
Okay.
This star C is minus 1 to the
Yes, yes, yes. I just want to take this through correctly.
No, this is like, so what you proved is gamma mu C transpose is gamma mu C. The full transpose.
Gamma mu C,
Full transpose is
gamma
gamma mu C.
mu C. C.
Then it reverses, right?
So
this is like C gamma mu. The reverse is what?
yeah, let me just do it. We'll go through it slowly. Sorry. Okay, I want this quantity. I want gamma 0 transpose C transpose. Okay. Now this quantity is the same as if I had just a C here. Yeah, that's why I wanted this, right? So I have this. This is the same as gamma 0 C times minus 1 to the power n into n plus 1 by 2. Gamma 0 transpose times this. Right? And now our relationship with gamma transposes was what? Was gamma transpose times C inverse. Okay. So this will be the same as, yeah, I'll just take this through. Gamma transpose times C inverse, I'll take that through. And so I will get minus 1 to the n, right? So this is the same as C times gamma 0 transpose times minus 1 to the power n to n plus 1 by 2 times minus 1 to the power n. You see, because the rule was that if you took a C inverse through, sorry, without the rule was that if you take a C inverse through, you reverse the transposition. But C and C inverse are off by a factor. So it didn't matter. You took C through, you also reverse the transposition. Okay, so far so good. So now we've got C gamma 0 gamma mu star C star gamma Z. This part is C times gamma 0 and then times this phase, minus 1 to the power n into a plus 1 by 2 minus 1 to the power minus 1 to the power n. Okay, good so far. Then we use CC star. C star T is identity. So this, let me write, yeah, fine. Is this into minus 1 to the power n into n plus 1 by 2, n into n minus 1 by 2. Excellent. So now we've got gamma 0, gamma 0, gamma mu star, gamma 0. Now let us remember, what happens, and we had a C, and we want the thing to, and we've got a C, right? So then we had this fact that we could take C gamma 0 through gamma mu, making it gamma, right? We use that somewhere. Let's remind ourselves of that. Okay, we had that gamma mu dagger is equal to well, gamma I dagger was equal to gamma I, and gamma 0 dagger was equal to gamma 0. Therefore, we had gamma 0, gamma mu dagger, gamma 0 was equal to gamma mu. Right? But dagger was equal to transpose times star. Okay, so we have gamma mu, gamma 0, gamma mu star transpose times gamma 0 is equal to gamma mu. Okay, and then by moving these around, we had this relationship with, this is, irritating. So what did I want? I wanted C gamma 0s. So I'm going to give you what I think is the right relation, and you tell me if you agree with it. C gamma 0 gamma mu star is equal to gamma mu C gamma 0. This is my my guess. Let me see if I got the sign right. Minus 1 to the power n minus 1. Thank you. Thank you. Minus 1 to the power n minus 1. Okay, excellent. Excellent. So, so now we've got gamma mu times C gamma 0 times gamma 0, okay, times minus 1 to the power n minus 1 times all those other minus signs. Now, those other minus signs, I believe, just a 1. Right, because n plus 1, n minus 1, 1. So that's just gone. Okay. Okay, n minus 1. Okay, and then this is equal to gamma mu times C times minus 1 to the power n. And so we've talked ourselves into trouble.
Sorry, what was C square? Like, is there any idea that C square is just?
Well, C square, we could find it. Sorry, so have I done something wrong here? I'm sorry about this. It's very.
That is 1.
Weren't those 1?
Yeah, that is 1.
Okay. I should have got gamma mu times C, both for n is equal to 0 and n equals 1.
That is minus 1 to the n square plus n.
Where?
It's not just 1.
Thank you. N squared.
No, but n into n plus 1 by 2, and then minus n, let's say. Instead of minus 1 to the power n, you take minus 1 to the power minus n. that makes it n into n minus 1.
Yeah, that's what I was also
and
thinking.
2 times n into n minus 1 by 2. So that is n into n minus 1. But that's an even number, right? Always. N into n minus 1 is an even number.
Yeah. One way of saying it is that we can, when there's minus 1, we can always make this minus 1 to the power minus of n into n minus 1. Then these two cancel up to minus 1 to the power n. So I've messed up somehow. Please, somebody help me. Kanu's got it right. Tell me what I did wrong.
So you can cancel the minus 1 n to the power n plus 1 with that other one you're saying?
Yeah, I'm saying that.
You get the minus 1 to the power n, right?
No, we got minus 1 to the power n into n plus 1 by 2 into minus 1 to the power minus of n into n plus 1 by 2. Because
That was n into n minus 1 or n into n plus 1?
sorry, minus 1. But I can put an overall minus sign because minus 1 to the power minus 1 is minus 1. Right? So this is equal to minus 1 to the power n by n, and that with the other minus 1 to the power n is 1. So that was just 1. But then we have this extra sign, extra thing from here. Let me check this. Oh, yeah, no, this sounds right.
Somewhere you wrote C inverse to C. You substituted C inverse to C.
Let's do that again. I didn't substitute C inverse to C. I just used the fact that if I can take C through and change transposition, I can take C inverse through and change transposition. But it wasn't like I changed C to C.
Oh, I see.
Yeah. I messed up. I'm sorry. Just give me 1 minute. Okay, let me do it again more simply. Okay, I'm trying to be too sophisticated, and I think that's causing me trouble. Does everyone agree that this is what we need to check? That sounds right? I'm going to start it again. Where should I do that? Let's just be less sophisticated. First, gamma 0 was an antisymmetric matrix. In our basis, gamma 0 is antisymmetric. So gamma 0 transpose is minus gamma 0. Okay, so we'll just use that. Gamma 0 transpose is minus gamma 0. But I want to interchange the order. So hey.
That you can change from front end. First C0 gamma, C gamma 0, you can also say.
Thank you. So fine. So the suggestion was this gamma 0, we're just going to make it, this is minus C gamma 0, gamma mu star C star times gamma 0 times C transpose. Now, C transpose was equal to this times minus 1 to the power n into n plus 1, but because of the extra minus, this is minus 1 to n minus 1 by 2. No. N into n plus 1 by 2, and then there's minus. Let's keep it. Okay. Now I take C through gamma 0. That gives that transposes, that's C gamma 0 transpose up to the factor of minus 1 to the power n to n plus 1 by 2. Was that right? Minus 1 to the n. Minus 1 to the power n. Again I use this, so that's minus 1. Okay, then I use CC star. So, I'm so sorry. This is the problem with supersymmetry in higher dimensions. The spinor algebra can be sometimes very frustrating. Sorry, but let's get this one right. And then fine. So then we use, so now let's keep track. So we had minus 1 times minus 1 to the power n times minus 1 times minus 1 to the power n to n plus 1 by 2. Then we use this guy. Cc star is equal to Cc star is equal to minus 1 to the power n to n minus 1 by 2. Okay. Then we take this through. And what was the factor? We get minus 1 to the power n minus 1. And now we should be through, right? We should be through. Sorry. Okay, and then there was a gamma 0 as well. There were two gamma zeros, and then we get an extra minus 1. Okay, now is this counting of signs right? Okay.
But gamma 0 also went through gamma star. Oh.
But C gamma 0 through gamma mu star makes it gamma mu times C gamma 0. Right? Could somebody else also check that this is the factor we got last class? Yep.
C star C and C star differ by minus 1.
It's a minus 1 for n minus 1. C gamma 0, if you take it to gamma star.
C gamma 0, it's minus 1 to the power n minus 1. Okay, the question was whether Cc star and C star C are the same. They have to be because they're basically inverses of each other.
C star is the C inverse.
Yeah. Yeah. Okay. Excellent. Now how are we getting the signs right? Sorry. This with this goes. Yes, we're still getting trouble, right?
No. It's fine.
Still, because there's an extra minus 1 to the power n from here.
No, but that's n squared.
No, n square is fine.
The other one cancels. Plus n by 2. N squared is left, right?
N square goes, right? Because we can make this minus 1 to the minus this. So this times this is minus 1 to the power n. The problem is we get 3 factors of minus 1 to the power n. What? Which is one factor, which is the same as we had down there. The extra minus extra minus sign is also going. We get the same answer as we got down there. What am I doing wrong? Sorry, give me 2 minutes. If we don't get it in 5 minutes, I'll clear up the algebra at home and show you next time. It's not worth doing so much of, but give me 1 minute. Let me check I'm imposing the right reality conditions. Okay, I'll take one last look and then we'll. Yes?
Is C star, CC star, is that right? The thing that you between CC star and n to n plus 1 by
Oh, thank you. It's n. That's the problem. Thank you, Siddharth. Okay. That cures everything, right? Because we get an extra factor of minus 1 to the power n. Okay. So thank you, Siddharth. Well, wherever we did it, so the minus 1 into n minus 1 by 2 goes to minus 1 to the power n to n plus 1 by 2. Okay. that cures it. Thank you, sorry about this. Sorry about this. Okay, okay, but it works. Okay, excellent. So, wonderful. So you see that this algebra also passes that reality check test, right? That the reality, that this is a consistent algebra. This algebra is consistent with the reality conditions. Okay. Now, as you see, we would sort of go, okay, what is the last thing we have to check? The last thing we have to check is that the algebra obeys all the Jacobi identities. Okay. That the statements make sense, just as statements of commutation relations we've now checked. However, commutation relations also have to obey Jacobi identities. If you remember, that's the first thing we checked in the first class of the whole course for the simple quantum mechanics algebra. This will be most of these Jacobi identities are actually quite trivial. Okay? Because most of the statements of the algebra are just that Q transforms like a spinner under Lorentz transformation. So Q commutes with P. Basically, the only real thing we have to check is the Jacobi identities involving 3 Qs. Okay? They are also essentially trivial because everything involving 2 Qs on the right hand side has a P or a central charge, and that commutes with a Q. So term by term it's 0. Okay? So checking the Jacobi identities in this case is not a very particularly difficult thing. Okay? I'm going to leave it to you to check this yourselves. Right? All the new things really are trivial. Okay? Everything else, for instance, the statement that M Jacobi identity with M with 2 Qs, that kind of Jacobi identity, that will be enforced by the fact that Q transforms like a good representation under M. And that the right hand side of the QQ anti-commutation relations respects that SOD symmetry. So everything else will be more or less guaranteed to work. But I'm going to let you check that carefully. Okay? So once you've checked the Jacobi identities, you've checked that this is a good algebra. Now, let's get back to looking at the algebra for a minute. Okay? So the algebra was here. The algebra was here, we wrote it down here. And what does this algebra say? It tells you that 2 equal supercharges square to momentum, appropriately defined. It tells you, on the other hand, that in general it could be that 2 unequal supercharges square to some number times something. C alpha beta times some number. Okay? These additional numbers are called central charges. Okay? Notice that the algebra is consistent as long as the central charge commutes with all supersymmetries, commutes with everything. As long as the central charges commute with everything, the algebra is consistent whether the central charge is there or not. Okay? So different theories with the same number of supersymmetries either will obey the algebra with z equals 0, or might obey the algebra with some antisymmetric or symmetric z, depending on whether n was 0 or 1.
By consistent, you mean they obey the Jacobi identity?
By consistent, I mean obey the Jacobi identity. I mean can come out of a quantum field theory. Right? It could have a quantum field theory in which you would have this algebra with z 0 or non-zero. Okay? These central charges, as we will see perhaps by the end of this lecture, certainly by the end of the next, can play an important role in representation theory. Okay? So the simplest supersymmetry algebras are just without these central charges. Sometimes the supersymmetry algebra with the central charges are called extended supersymmetry algebras. Okay? The simplest supersymmetry algebra is the one that is most analogous to the ones we studied in quantum mechanics have z equals 0, and that's consistent. Z non-zero is just an extension of that same kind of algebra. Okay. The next thing we can ask is the following. Okay. The next thing we can ask is suppose Z was 0. What transformations of Q will keep the algebra invariant? Okay? What transformations of Q will keep the algebra invariant? What field redefinitions of Q will keep the algebra invariant? Now our Q's are spinors, and we don't want to change that fact. So these field redefinitions, these transformations, these linear transformations we're looking at will be transformations of the form Uij Qi alpha is equal to Uij Qj, let me call it Uij, Qj alpha, something like this. Okay? But these transformations have to have the property that they are consistent with the reality conditions. Okay? The reality conditions have stuff acting on the spinors. Okay? The reality conditions had stuff acting on the spinors. But as far as the ij indices were concerned, was just Q star is equal to Q. Okay? So as far as the ij indices were concerned, Q were basically real numbers. Okay? So we want to do this kind of transformation. We want to keep these guys real numbers. Okay? And we will want to keep this delta ij conserved. Okay? So these U's, basically this tells us that U's will be SON matrices. You know, had it not been for had we allowed complex numbers, we would have allowed for unitary kind of matrices. Okay? So is this clear? So what we would have is if Uij, we want Uij times Ujm from this being invariant, Uij times U transpose Jm, Uij. Okay, so let's just act with these U's on this. So we get a Uij and a U transpose from the other side acting on this guy. So we need the matrix that, let's say, O times O transpose is equal to 1. Okay? And that gives you the condition that the matrices also have to be real. And that tells you that they are SON matrices. Is this clear? Okay. So what this is telling you is that this, what people sometimes call automorphisms. Okay? The set of redefinitions of supersymmetry in this dimension. Okay? Which will preserve the commutation relations. Okay? The set of redefinitions of supersymmetry in these dimensions that will preserve the commutation relations are SON, where n are the number of supersymmetries. Ys? Oh, it could be On. Could be On. The difference between SON and On is just one element. On is fine. Okay? We normally think of the infinitesimals. So that for that there's no difference. On, you're right. On. Yeah. You see, our algebra has the feature that we're taking bilinear and getting linear things on the right hand side. You do a nonlinear transformation, it'll muck up that it won't be an algebra anymore. Right? We want commutator of two elements is a linear sum of elements. So that structure needs to be, can only be consistent under itself under linear transformations. Is this clear? Excellent. Now, this set of these automorphisms have a name. They're called R symmetries. Okay? So what we've discovered is that the R symmetries what we've discovered is that the R symmetries of this algebra for R SON. This is true in D is equal to, what was it? 1, 3, 9, 12, so on. Thank you. 11 and so on. Okay? One little word about R symmetries. R symmetries are the maximum group of transformations acting on supersymmetries that could leave the superalgebra invariant. Okay? Now, in a physical theory, there may or may not be a physical R symmetry charge. See, R symmetries are not part of the superalgebra. It's just that if you ask the question, I'm looking at a physical theory, it implements the supersymmetry algebra, and can it have any other symmetries that interact non-trivially with the supersymmetry algebra? That act non-trivially on the supercharges. Okay? The largest possible group of that is this SON, but there's no statement that this SON has to exist. Okay, a particular physical theory may not have an SON charge that allows for rotation of these charges. Okay, I say this to contrast with what we will see when we study superconformal algebras, when, as you will see, these R symmetries will appear on the right-hand side of the commutation relations. So in superconformal algebras, physical theories which implement these superconformal algebras have to be invariant under R symmetry. Is this clear? Please. What? Well, the question is only if you perform an ON transformation on these on this algebra, does it leave it invariant? That's the mathematical question we're asking, and the answer is clearly yes, because O times O transpose is equal to 1, whether the matrix is SON or ON. So at the level of this automorphisms, it's clearly ON, as Sunil was just right. Now the question of whether a physical theory actually has either an ON symmetry or an SON symmetry or no symmetry at all, that is another matter of the physical theory. This is just the most general thing, other symmetry one could have that interacts in some non-trivial way with the supersymmetry algebras. Okay, so maybe what I should say is this, that I could say this in another way. The supersymmetry algebra I've written down here could be extended to Mij, okay, Q, so let's say M, Q, I, okay, M, A, T, A, M, A, Q, I is equal to is equal to the M in the So suppose I write this whole thing as MATA. So it's some abstract group element written like MATA. Okay, this will be in the fundamental representation. So this is what I want. It's TA fundamental times IJ QJ. Yes. So another way of saying what I said previously is that the supersymmetric algebra can be further extended to include a bunch of new charges which are SON generators. The only new non-trivial commutation relation in this extended algebra is the commutation relation between the SON charges and the Qs.
These commute with E and M.
These commute with everything else. These are just the flavor indices of which supersymmetry. Okay? So another way of saying what I was saying is just like we had this extension with the central charge, there's another extension to include a few more generators. These are the generators of SON. SON commute with supercharges in the way to make them transform like fundamentals of SON. Okay? Now, this algebra is as consistent as the early algebra. And it could be that the physical theory will implement this algebra with new symmetries which are M's of this sort. Could be that the physical theory will have only SO2 or SO3 even though N is 5. Okay? The M's are not necessary for the consistency of the algebra, but is the thing that you can add to it, a thing you can add to it without ruining the consistency. Okay? So these SON charges are physical symmetries, that the most general physical symmetries that can be added to the theory and have non-trivial commutations with the supersymmetry algebra without messing up the algebra.
So you're saying that the extensions can be only SO and the maximum is SON?
Exactly.
It can be SO2, SO3 and then after SO.
Exactly. Yes.
No, I was asking
Yes.
subgroup of SON.
Yeah, it's fine.
It is valid for any Zij.
Good. Now the question is what happens with Zij? Okay. Zij has two indices under this ij. So you would have to supplement it with a rule saying that Mij commutes non-trivially, has a non-trivial commutator with Zij and makes it transform in the two index symmetric or two index anti-symmetric representation of SON. Okay, so now, if you have this R symmetry, the Z is not completely central anymore. In the sense that it doesn't commute with everything. It has a non-trivial commutator with the SON charges. But other than that, the algebra is unchanged. Okay, excellent. Yes, question?
Yeah, I was asking that time was, let's say there is a physical theory that has this kind of commutator thing without that Z.
Yes.
And Q transforms like that. And A priori can be ON. So what then decides the extra constraint that it will be SON?
The physical theory may have a new ON symmetry or it may have an SON symmetry. This is a matter for the physical theory. Algebra does not help you there.
The constraint comes from what? Like what should the Q be?
It's not a question of Q. It's a question of whether the charges for that theory, for instance, the O2 part, the non-trivial element of that ON symmetry might turn out to be anomalous in the actual theory. This is a matter of dynamics.
Okay, so at this stage there is no.
Algebra does not help you there. As far as algebra is concerned, you're on your own. This is a matter for which theory you're studying. It's a detailed question. Okay. Other questions or comments?
But if a theory has this algebra,
Yes.
any point of the theory, then isn't it guaranteed to have this symmetry?
No, we will see many examples.
Because then I can just take these linear combinations and those also.
No, but the question we are asking is not that. We're asking, is there some field redefinition we can do on the fundamental fields of our theory?
Not just
Yeah, everything, right? Okay, and that may or may not happen. We will see many examples as we go on, which some of these R symmetries becomes anomalous, or they're broken or something. What does it lead to?
What else does it give that was not originally there?
What else does it give that was not originally there? We'll see some of this as we go on. In fact, possibly in today's lecture. But one thing we will see is the following. We will see that when we look at the representations of supersymmetry, as we will see as we go on, we will see that massless representations of supersymmetry are shorter, smaller than massive representations. Okay? However, in special cases where you have this R symmetry, you have special short massive representations, which are called Bps representations. Okay? And these special short representations play a very important role in calculability in many theories. Okay? So this R symmetry can sometimes be very important. Also, as I said before, when the theory becomes superconformally invariant, these R symmetries become part of the algebra in the sense that the R symmetry appear not just on possible left-hand side of the algebra, but also on the right-hand side of commutation relations. So that the algebra becomes inconsistent without the R symmetry being a symmetry of the theory. Okay? And so that becomes really an important part of dynamics. Again, we will see much of this as we go on. Okay, other questions, comments?
About the comment that Suman made
Yes.
in the beginning, if we didn't have delta ij but some other matrix,
Okay.
it would be SON.
Then that would not be SON, but now let's go back to Schumann's comment. Let's go back to Schumann's comment and look at this. Okay, Schumann was asking if we have if we have Qi, Qj, and I'm omitting the spinor part. It's irrelevant for this discussion, right? Suppose we had this times Sij. Oh, let's call it Pij, Qij, Zij. Okay. Now let me perform a similarity transformation on Qs. Okay, so zeta goes to S zeta S inverse. Or sorry, S zeta S transpose. Okay, so now we are going to ask, now the question is, what can you do to zeta if you are allowed to similarity transform this guy? Let's say there are similarity transformations only by real matrices, because we don't want to mess up reality conditions for Q. So we take zeta to S zeta S transpose. Now, let's see. Yes. Doesn't look very much like, because this is in this internal space, and M and M act only on the spinors. Hang on for 1 minute. I mean, of course, as Schumann said, it would have had to be symmetric. Now, I'm looking at the most general symmetric matrix, and I want to see what I can say about that up to similarity transforms.
Usually, this kind of thing for set is you diagonalize it and then divide Q by numbers, like diagonals.
Should we say that zeta does not change under this similarity transformation?
I see. Give me 1 minute. Right. Under this kind of transpose transformation, you want to know whether what canonical form we can put zeta ij into, right? That's the question. If it's ON S transpose, okay, good. Right, but we shouldn't take on. So another way of saying it is this. Let's start with zeta equals identity. And let's start with the most general similarity transform. Okay, most general linear combinations of Q, and see what identity can become. So that would be the forward way. Right, so as you say, the ON part will sort of be trivial. That'll leave identity unchanged. So isn't it true that the most general matrix can be written as A times O, where A is Hermitian? In general, there's this decomposition, right? Maybe we should do this offline, actually. There's something to say about it. Okay, let's do this offline so that we don't. I'll come back with an answer next class. There's something to say about this. Okay, I think that we can largely fix it to this form. Anything that's not of this form, of course, won't work. But I'll try to tell you why. Is symmetric, and then the question is whether the most general symmetric matrix can be written in this form, right? And I think it can. I think it can. I think that the most general symmetric matrix can be written like this. So I think you can always bring this back to this, but I'll confirm this and get back to you guys. Okay, excellent. Excellent. Okay, so now, so far what we've done is to look at the algebra and these strange dimensions. In dimensions, what was it? 1, 3, 9, 11. Let's move on to other dimensions. Okay, so let's move on to dimensions. Let's stick to odd dimensions for a minute, but move on to the pseudo-real dimensions. So let's move on to D is equal to 5 plus 7 is 13, 7 plus 15. Okay. Here the algebra is Qi is equal to gamma alpha C, so P slash C, P slash C, okay, and now we have something sort of interesting. We have an omega ij, okay, plus C z ij. Okay, now what is this omega ij? Okay. This omega ij here is the following matrix. Remember that in these dimensions, what is different from D is equal to 1, 3, and so on. In these dimensions, our spinors cannot be completely real. So they cannot obey they do not obey the condition. They do not obey the condition. They do not obey the condition. They cannot be made to obey the condition Q alpha is equal to C gamma 0 Q alpha star. The reason they don't obey this condition is that when we act on this twice, we get -1. We get the condition Q is equal to minus Q. Okay, and as we discussed earlier on, that can be changed if we have I and J, okay, and a matrix omega ij. Okay, we have a matrix like this. We impose a condition like this, where omega ij, omega is a matrix such that omega squared is equal to -1, and omega is antisymmetric. Okay, you should think of the canonical form of this omega as being given by 0, 1, -1, 0, 0, 1, -1, 0, and so on. Okay, so in these dimensions, the relationship that we have, the reality condition that we have, that we are allowed to impose and that we choose to impose, is this one, the one I've written on the board there. Okay, but if we choose to impose these reality conditions, two things have to be reassessed in this dimension. First, there is the question of First, the question of whether the transpose is working out. Okay? And second is the question of whether the reality condition is working out. Now, for the question of whether the transpose was working out, the algebra we did basically did not depend on dimension. Right? We got this quantity here, which did not depend on, which was true for any n. Right at the end, we put in that n was either 0 or 1. Okay? Now let's work this out for n is equal to, this is effectively 2 or 3. So let's work this out for n is equal to 2. So this is 1. But this is 2 into 3 by 2, so that's 3, so that's minus 1. So the transpose was not working when n was equal to 2. Similarly, when n is equal to 3, this is minus 1, and this is 3 into 4 by 2, so this is 1. So this algebra again was not working in n is equal to 3. Okay? So if we were thinking ahead, we would be worried. What happens to the supersymmetry algebra at n is equal to 2 or 3? But you see, now we see the resolution of this question. Because this omega was antisymmetric. So the condition we required from the transposition was the reverse of the one we required earlier. Right? Because omega itself picks up sign under interchanging ij. Okay? So we already see that the potential problem in this algebra is resolved by adding this omega ij here. Okay? And in a similar way, the potential problem in reality, okay, will also be resolved by adding this omega ij here. Okay? I'm going to leave that to you to check that working. Okay? So try imposing the reality condition. Okay? Try imposing the reality condition using the fact that omega squares to minus 1. Check that in these dimensions also that works. Okay? You have to impose the correct reality condition, right? We have to now impose a reality condition involving also an omega. So you have to just do that carefully. I'll leave that for you to check. Okay? Great. So, last question is, what about the symmetry or antisymmetry of these z's? Okay? So for that we just needed to know how C transformed under can somebody find the C transposition rule? C transpose was n into n plus 1 by 2, right? Yeah, was equal to C times minus 1 into n to n plus 1 by 2. Okay? And so in d equals 2, n is equal to 2, so d equals 5. This is 2 into 3 by 2. So that's odd. So, and so Zij would have to be antisymmetric. Whereas n is equal to 3, this would be 3 into 4. So that's even. 4 by 2, so that's even. So n is equal to 3, we get even. And so we conclude that for d equals 5, Zij is antisymmetric, and for d is equal to 7, Zij is equal to symmetric. Okay, let us check this. Symmetric, antisymmetric, correct. Okay. Now, we can ask, what is the R symmetry in these dimensions? Now, remember last time we got the R symmetry from the condition that it was the symmetry operation that preserved reality conditions and left delta ij invariant. Now our condition is that it preserves the appropriate reality conditions and leaves omega ij invariant. But does anyone know the name for a group that leaves omega ij invariant? SP. Okay. So now the R symmetry group is SPN or SP2N, and people use different conventions for what they call what. Let's fix a convention so that we don't confuse ourselves. If we have, because our number of supersymmetries in this case is always an even number. Okay? So our number of supersymmetries is equal to 2n. And let us call the group that leaves this matrix with 2n entries invariant, let us call that group SPN. There are two different or almost equally used conventions in the literature where some people call this SPN, some people call it SP2N. Okay? With our conventions, SP1 is a non-abelian group. I mean, SP1 makes sense. With the other convention, SP, you have an even number always. Okay? SP1 as a group happens to be, at least as Lie algebra, happens to be isomorphic to SO3. Okay? So with our conventions, SP1 is SO3, and I believe SP2 is SO5. In my convention, I believe SP2 is SO5. I will check that. Okay. It often happens for these, at low ranks, these groups become equal to each other, right? In the same way that SU4 is SO6. At least at level of Lie algebra. Yes?
There are only n supercharges, right? Qi.
There are 2n supercharges. You see, because our reality condition was Qi alpha was this. So the reality condition was, this one. That Qi alpha was this stuff times omega ij. Omega ij was a matrix acting on a 2n dimensional space. So I runs from 1 to 2n. This whole thing doesn't make sense if the number of supersymmetries is odd. Because there's no omega ij matrix if the number of supersymmetries is odd. Is this clear? You see, every antisymmetric matrix, this has equal, for this condition to be met, that omega squares to -1, okay, and omega ij to be antisymmetric, that condition is only met when the dimension is even. Let's try. Let's try to find a 3 cross 3 matrix. Is this your question, Kanu? You got it? Okay, fine. Maybe I'm not. Does somebody else have a confusion? Was this clear? Okay, excellent.
So for other dimensions, number of charges can be n.
For 1 and 3, number of charges could be odd. Could be 1 supersymmetry, 2 supersymmetries, 3 supersymmetries, and so on. But when the charges are pseudo-real, by the nature of pseudo-real charges, the number of charges is even. Right? That was the point of charges being pseudo-real. By trying to put a reality condition, you see the most general kind of charge is complex. One complex is 2 real. By trying to put a reality condition, you're trying to deal with odd numbers of real charges. Pseudo-reality is the statement that you tried but failed. So you have some sort of reality condition, so you're dealing with sort of real spinors, but you have to deal with them in pairs. Is this clear?
Is there any necessity for imposing pseudo-reality?
You could just deal with complex spinors if you want. You could do that. But this is the...
Then there is no balance.
Yeah, but the reason that you want to deal with reality conditions is you want to know what charge is the complex conjugate of what other charge. In the quantum theory, this is very important because you want to know what is the Hermitian conjugate of what. Okay, and in representation theory, that will play a very big role. So it's very convenient to think of it. This way. Okay, excellent. Let's keep going. So we've completed our scan of all odd dimensions. Okay. Now we move to even dimensions. The main new element in even dimensions is that spinors can be chiral. Okay? Oh, we're out of space here. Let's go down here. So you remember we had three kinds of even dimensions. The simplest kind was D is equal to 2, 10. In this dimension, spinors could be real and chiral. Chiral spinors could be real. Okay? Therefore, supersymmetry now is defined by two integers, n plus and n minus. The number of chiral supercharges and the number of antichiral supercharges. Okay? So in every odd dimension, I just have to tell you the number of supersymmetries. Here I have to separately tell you how many chiral supercharges we have and how many antichiral supercharges we have. Is this clear? Okay. So now let us write down the algebra.
Sorry, what is the nth of the element?
So in 10 dimensions, chiral spinors can be made real and antichiral spinors can be made real. So how many supercharges do you have that are chiral spinors, real chiral spinors? And how many supercharges do you have that are real antichiral spinors? Okay? Could be even or odd. That, yes, because it's real, there's no pseudo-reality condition. So each of n plus and n minus can be even or odd. Okay? And so let's write down the algebra and then we will discuss it. So Q plus I, Q plus, okay, now notation becomes a bit irritating. I, J. Okay, this is equal to 1 plus gamma D plus 1 by 2. But plus is telling you that these are the positive chirality spinors. Maybe I'll put the plus up here. Plus I plus J. Okay? This times P slash times delta Ij. Okay. Q minus I alpha. I really should use some different notation for this tilde. I'm just using alpha. Okay. Q minus J beta, okay, is equal to 1 minus gamma D plus 1 by 2 P slash O, and of course C. Let's call this Mn. Okay, and finally, there's the anti-commutation relation between Q plus alpha I, Q minus J beta. Okay, and this guy is Okay, they want me to do minus and plus. I'll do that first. Oh, it doesn't matter. Okay, but it's just which one has the index here. 1 minus gamma D minus D plus 1 by 2 times C times Zij. Sorry, say again. Okay, so what does this algebra say? It says that Q plus with Q plus squares to momentum. Q minus with Q minus squares to momentum. Q plus with Q minus squares to potentially a central charge. Okay. Now, various questions we want to ask here. First question you could ask, I mean, there's so many questions you can ask with this algebra. Let me start with one random question. The first question you could ask is, why couldn't we have had a central charge in the Q plus commutation relation? What's stopping you from doing that? Certainly it's not symmetry properties, because then we could add like some Zij and then change its symmetry to make it whatever you want. And the answer to that is that if you've got a central charge, then the Q commutation relation is just with a C. Now something consistent has to happen, right? You see, because the spinner has to be chiral, both the alpha index and the beta index has to be chiral. Okay, so let's try that out. Suppose we had up here, okay, suppose we had up here added a term which was some alpha ij times C alpha beta. Could this have been consistent? Okay, well, you see, this object had to have the property that if I take it and I act with 1 minus, so if I act with 1 minus gamma d plus 1, I act with 1 plus gamma d plus 1 by 2 from the left, it leaves the commutation relation unchanged, because Q acting from the left leaves the commutation relation unchanged. But now I want to take this thing through C. Okay, now when I take this through C, remember what this gamma d was, gamma d plus 1 was. Gamma d plus 1 was a bunch of gamma, was the product of gamma matrices, gamma 1 to gamma 2n, times some I to the power something, which will play no role. Okay, now when I take this C through this, it transposes each guy in this and picks up a phase, but the phase appears an even number of times. So the phase cancels. So so when I take the C through, this becomes C into 1 plus, and this quantity now has everything transposed. Okay, this quantity now has everything transposed, and this quantity now has each gamma transposed in this kind of order, right? Gamma 1 transpose, gamma 2 transpose, gamma 2n transpose, times the same I to the power n that we always do, whatever. This factor has not changed. Maybe we called it I to the power n minus 1 for the Lorentz group, times C. Is this clear? It just term by term transposes these. Oh, in fact, we knew how this guy commuted with this gamma d plus 1. Can somebody pull that up? What? Say again? Is equal to minus 1 to the power? Minus 1 to the power. N plus 1. Excellent. 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 This one was transposed, right? Okay. So this tells us that we get 1 plus gamma of d plus 1 transpose by 2 with a C. With a C. Yeah, I don't think transposition properties changed at all. Something is wrong. Give me a minute. Was this minus 1 by n or? Just a minute.
Is gamma d plus 1 symmetric?
No, I wanted it with minus. I wanted this thing with the trans. You see, sorry, what was I after? I was after saying that if I multiply with 1 plus gamma d plus 1 by 2 from the left, this leaves it invariant. And also if I multiply by 1 plus gamma d plus 1 by 2 on the right, but with the transpose, that should leave it invariant. Because both of these guys were chiral spinors. Okay? So what I expected is when I took this 1 plus d plus 1, gamma d plus 1 by 2 through C, it would become 1 minus gamma d plus 1 by 2 transpose, and therefore kill, tell you that the thing was inconsistent. Give me one. I'm so sorry for the incompetence with the gamma algebra. Give me 1 minute. Why is that not working? It also tells us we will have trouble with this. I was going to do the next thing with that guy. We would have the same. What? Why did I pick a sign? Small n, we are dealing with n equals 4. You're right. Thank you. We're dealing with n is equal to 1 of 5. Thank you. That's it. Thank you. Okay. So we got. Thank you. So we get this, but with a minus sign. Okay. And therefore, this is inconsistent. Do you see? Let me say it again. What we have from the expression of the top guy, we have P plus on Q alpha I, Q beta j is equal to Q alpha I, Q beta j. This is true by definition. On the other hand, P minus on the same object is equal to 0. We also know that this object times P plus transpose is equal to the same object, but the same object times P minus transpose is equal to 0. This follows from definitions. Okay? So now what we have shown is that if we take P plus on C, that is equal to C times P minus transpose. Okay? So since P plus on C is this object, but that's equal to C times P minus, which is 0, this object must vanish. Right? So it would be inconsistent to have a term in the algebra that was just C alpha beta up there. Thank you, Kanu. Thank you for helping me. Thank you for getting the algebra straight. Is this point clear? That if you multiply from the left by the projector onto the chiral spinner, that is by gamma matrix algebra the same as projecting the right spinner into the antichiral sector. Is this clear? Because we take P plus from the left through, you get P minus transpose, which is the projector to the antichiral sector on the right. This tells you, this is precisely why this is a consistent term in the algebra. Because we acted with the left projector on the left, okay, and we took it through the C. So this could also be written as is equal to C times 1 minus gamma d plus 1, 1 plus transpose by 2 Zij. We just checked that. Sorry, what were you saying?
No, C will be on the...
I've moved it through. I've moved C through and got this. What? Gamma is... well, I mean, why do you say that? I moved C through. So this times C is equal to C times this. Gamma d plus 1 transpose is gamma d plus 1, that may be, but that's not relevant. Because we want to act with the projector from the right. So we have to act with projector transpose, right? Okay. Right? Right, here in all these conditions I put P plus P minus, P plus transpose, P minus transpose. That's the correct equation to impose. Okay, so what? It doesn't matter. Is this okay? So the central term on that there is consistent with chirality. Whereas a central term with just plus plus spinners or just minus minus spinners would not be consistent with chirality. Similarly, you could ask.
So you're saying put P plus and P plus transpose and this left and right.
Yes.
And then if you calculate that will become
0. Exactly.
That will not be an identity.
What?
It should have been an identity.
It should have been just itself.
Yeah, itself.
But if you get 0, therefore the only thing you could have had was 0. Okay. Similarly, we can ask these terms here. These terms, are this term and this term now consistent with, this term and this term now consistent with chirality? Okay. And now we see that they are. Okay. Because you see, suppose we write P plus times gamma mu times C. This is equal to P gamma mu times P minus times C, because gamma d plus 1 anticommutes with everything. This is clear? Gamma d plus 1 anticommutes with everything, so taking a gamma mu through changes P plus to P minus. Okay. Now is equal to gamma mu C P plus transpose. Is this clear? And therefore, these two terms in the algebra are also consistent with chirality. Okay, so at least chirality we have checked. Okay, now we have to do many more checks. We have to check that, you see, the last term has no check from transposition, because that is an anticommutator between two different kinds of objects. Okay, transposition is a check if you do transposition and you get back the same kind of thing. Okay, what we got in the last term is Q minus anticommutator with Q plus. If you do the transposition of that, it will tell you what the anticommutator of No, I said saying it wrong. Yeah, but okay, there's some ij business here. No, it's sorry. I said it wrong. The ij, I said it wrong. Q plus Q minus alpha beta. Then alpha beta if we change and ij we change. Because we're doing anti-commutator. It doesn't change the left hand side. That's true. So that will tell us about the symmetry of Zij. Okay, and we'll come to that. But we should also check the transposition properties of the first two terms, just to check that they are working. Right? That the transpose of the first guy is the second guy, that it has the right transposition properties. Okay, this check will be basically as we've done before. Okay, in fact, we've done the algebra on the board because the algebra is not changing. It didn't change n by n. So I'm going to ask you to go and check that it's all okay. Okay, we do it. I'll get it wrong, then you'll correct me, and it'll take forever.
Sorry, for the first two, you can check it.
We can check it. Even for the last one, we can check, and we'll see whether we get Zij equals even or symmetric or antisymmetric. No, symmetric. It'll be. Yeah. You're right. For the first two, there is a clear check, and
also it is true because
yeah. For the last one, there's nothing to check because alpha on minus is different from alpha on plus. Thank you, Shuman. Yes. Right. For the last one, there's nothing to check. I agree. Yes. Sorry. What were you saying?
No, I was saying that for the first two, as Chintan said, gamma d plus 1 transpose is.
Gamma d plus 1 transpose, but there's also a C. There's P slash and C, right?
But you are saying for these dimensions you have to prove that gamma mu C is.
We have to take the whole thing, transpose it, and show that it comes back to itself.
For this kind of dimensions.
For these dimensions. Okay? We've essentially done that algebra. You just have to work through it again carefully. It works out. Oh, just one sec. Once again, there's a reality check also. Okay? That again, we have essentially done the algebra. It's the same thing. You have to go through it again and check that it works. It works out. Okay? Yes, Kanu.
There is another commutator, right, which will be Q plus I alpha and Q minus the beta, which will be.
Yeah. So that's what we will. Right. So what is the. That is just interchanging alpha and beta. Correct. And that is consistent because of that. So let's write down in an equation what you're saying. Kanu was asking, what can we say? What can we say about Q plus alpha I, Q minus, we probably want to call these slightly different things. Minus I'll call M, Mj, right? Because this is an index for which antichiral spinner, and this is an index for which chiral spinner. Okay, so you had Q plus alpha J, Q minus M beta. This is your question, right, Akanu? Wait. So first, it's clear that whatever we get here will just be the transpose of this. Because it is just interchanging alpha and beta in this.
Keeping minus and plus in the left and right.
Doesn't matter, it's an anti-commutator. AB plus BA is same as BA plus AB. Clear? See, with the commutator it makes a difference of a minus sign. Then anti-commutator makes no difference. Okay, so whatever we get is just the transpose. It's just whatever we have here, we interchange alpha with beta and beta with alpha. Okay, so we just have to take the transpose of this, and whatever it is what we will get. Now, you see, another way of saying that is you read it from right to left rather than left to right. And this equation here is telling us that if we read it from right to left, this P minus has become a P plus. Okay, so it's consistent. It's just that transposition is changing this P minus to P plus. Is this clear? Okay, excellent. So there's no new information. There's no new information that we've not already got trivially. Okay, excellent. So both the reality check and the transposition checks I will leave to you as an exercise to check. Is this clear? Is this okay? Please, Sunil. Z, good. What can we say about Z? So first, the question that you can ask is, there's no condition. There's no condition. Okay? And the question you can ask is, what is the R symmetry? The R symmetry is clearly SON plus times SON minus, because you can separately rotate the pluses and the minuses. And this Z here transforms like a bifundamental of SON plus times SON minus. There's no condition on Z. In particular, the number of pluses and minuses need not even be the same. So it doesn't make any sense to have a symmetry or an anti-symmetric kind of condition on Z. Okay, so Z is now completely free object. Okay, excellent. If you guys don't mind staying like 10-15 minutes extra today, we'll complete the algebras. We won't be able to go through the representation today, but we'll discuss all the algebra. Nobody has a clash? 10-15 minutes more? Perfect. Okay, excellent. Okay. Maybe we'll start on this point. Sorry, louder. From dynamics. And the algebra is also different. So you have a genuine algebra for every value of n plus and n minus. These are distinct algebras labeled by n plus and n minus. In the odd dimensions, the algebras are labeled by one integer. Now in this case, it was labeled by 2. Clear? Okay. Okay. Now let's look at the dimensions where spinors are still real, but pseudo-real. I mean, spinors are still not complex, but they're pseudo-real. Okay. This was the dimension 6 and so on. So in D equals 6, 14, 22. What does the algebra look like? Well, sort of very similar. Q plus I, Q plus J alpha beta is equal to, any guesses? What should I write? Somebody say? P plus alcohol, then go on. Perfect. P slash C alpha beta and omega ij. No, we call this omega plus ij because Q plus Q minus alpha, Q minus J beta. Let's call this M and N. Okay, is equal to P minus P slash C alpha beta omega minus ij. Well, this omega, the number of ij indices here and the number of ij indices here are different. Mn indices here. This could be a 4x4 matrix. This could be an 8x8 matrix. So, distinguish. Okay. And Q minus I, no, Q minus M, I don't know why it writes minus first. Q plus I, alpha beta. This is equal to, okay, any guesses? What P should I write here? P minus, because the first guy is a minus. Okay. Then I, of course, want a C alpha beta and a Z mi. Now, once again, okay, n here was equal to 3 or 7 and so on. Okay? So once again we should we should ask the question of what happens to P as we take it through P slash and C. Kanu helped us last time to say that, helped us to conclude that P plus times C was equal to P minus transpose C times P minus transpose. Right? Because we got this fact from the minus 1 to the power n. N continues to be odd here. Okay? So once again, P plus times C is equal to C times P minus, C times P plus transpose. P minus transpose, because n was odd. Let me write that equation. So we have P plus times C equal to C times P minus transpose, but P plus times gamma mu times C, okay, is equal to gamma mu times C times P minus P plus transpose. The algebra is the same as for the earlier dimension, because the only place we used the dimension was minus 1 to the power n was minus 1. And that continues to be true here. Okay, so we see that this is consistent. Because we can take this P plus through and it remains P plus transpose, which is what we needed because this and this were both chiral. We see that this is consistent because we can take the P minus transpose through and it becomes a P minus transpose. And that's consistent because this and this were both antichiral. And we can see that this is consistent because we can take the P minus transpose through and becomes a P plus, and that's a P minus through and becomes a P plus transpose. And that is also consistent because this was antichiral and this was chiral. Just the same thing as before. All it used was that n was odd. Continues to be true. Okay? Once again, the transposition and reality, I'll leave you to check. Okay? So in this case, what is the R symmetry? The R symmetry is Spn plus times Spn minus. Okay? And Zim transforms as a bifundamental under Spn plus times Spn minus. All clear? Okay? Finally, there's one algebra left. One set of algebras left. Bifundamental. So its first index transforms like a fundamental index of Spn plus. Yeah, maybe, yeah. And the second index is a fundamental index of Spn minus. Such a thing is called bifundamental.
You can't actually talk about symmetry or asymmetry.
Because they're just different objects.
Totally different things.
Yes, exactly. Thank you. Perfect. So the last dimension that we need to worry about is 4, 8, 12, 16. These dimensions are special because spinors were complex in these dimensions. Okay? So, in these dimensions now, we do not have separate chiral and anti-chiral spinors. Because if you have a chiral spinor, then its complex conjugate is an anti-chiral spinor. So you have the spinor and its complex conjugate. You have as many chiral and anti-chiral spinors because you've got the spinor and its complex conjugate. Okay, so we might as well deal not with chiral and anti-chiral spinors, but just chiral spinors and their complex conjugates. Okay, so I hope that's how he's presented the algebra. Let me see. Okay. Yes. Okay. So in these dimensions, we will only deal with the positive spinors and their complex conjugates. Okay? If we had a negative chirality spinor, if we had a negative chirality supercharge, well, we'll just redefine it so that its complex conjugate is the supercharge of interest. And we'll call that a positive chirality spin. And this will then be the star of the earlier one. Right? So we lose nothing by dealing with only chiral spinors. So let's let the spinors, which are now always chiral, I'm going to remind you of that they're chiral with a plus in the notation. Let the spinors be Q plus I and Q plus J. Okay, and I will sometimes take right. I will sometimes take Q plus bar. What I have to do is to give you the commutation relations between Q plus I alpha and Q plus J beta bar. Okay, where bar was complex conjugate and multiplication by gamma 0. No, not C gamma 0, just gamma 0. This becomes a spinor with index up rather than down. C is to lower the up index. I'm not doing that. Okay? So I want to give you the commutation relations between gamma plus I alpha and gamma bar plus J beta. Okay. So this is P plus claim. P plus P slash. Now this here for the first time we will have upper and lower. Is it worth it? This guy is a lower index. I'm putting it up here so that you don't get confused. But it's a lower index under the R symmetry, which in this case, first time we have a complex group, which will be SUN or UN. Okay, because of this bar, this will be a lower index. I can't hear you. Beta will also be upper, correct. Beta is also up. Yeah, so you want me to put the J down here? Come, let's do that. Okay, great. Beta will be up, correct. So we have P plus alpha beta, no C, because we have one lower and one upper index. Okay, and we have delta I J. Okay, and what remains is to obtain Q plus I alpha and Q plus J beta. Okay, and this will be P plus C alpha beta times Zij. Okay. What is the R symmetry here? The R symmetry is clearly, now the i's run from 1 to n. R symmetry is clearly UN. Right? Because it's a set of matrices such that that leave delta ij invariant, but with no particular restriction on being real.
So what happened to bar and q bar?
Q bar and Q bar? Well, that you get by taking complex conjugate of this. Okay? So I'm not writing down as an independent relation, you can figure it out from what I've written. Okay? So the independent information is these two things. Okay. Not in the first one. Because this is gamma Q bar. Okay? That means gamma 0 times Q star. Okay? And that has an upper index. Therefore, there's no C needed. Okay? Now, various things that one should check to make sure this algebra makes sense. One has to check that it's consistent with chirality. One has to check that it's consistent with transposition, and one has to check that it's consistent with reality. Okay? What about chirality? So, for chirality, okay, for chirality, what is the thing that we need to check? We need to check that P plus times P slash, okay, that P plus times P slash behaves the right way. So now what is the right way? We know that if Q plus is chiral, Q bar is anti-chiral. That's why we were in a dimension where the spinors were complex. Okay? So the thing we need to check is that P plus, that we multiply here with P plus, but if you take it through here and multiply on the right, it gets multiplied with P minus. But that's obvious because this P slash changes P plus to P minus. Right? Because every gamma matrix anti-commutes with gamma d plus 1. So 1 plus gamma d plus 1 by 2 times gamma mu is gamma mu into 1 minus gamma d plus 1 by 2.
It should not be P minus transpose, right?
Oh, P minus transpose. Yes, you're right. It's, no, well, let's. Now, yeah. I think you're right. Because it's an upper index, it's actually just P minus. So let's look at that. What we really want to do is to take this and make it once again a spinor with a lower index. So we want to do, what we really want to do is to multiply by C and then check that it gives you the P minus transpose. Okay? Now let me check that. Right. So we want to take this. So the question is, if we do the following, if we take Q alpha, if we take the right hand side, multiply by C,
Shouldn't we multiply by P minus transpose?
what, sorry?
Shouldn't we multiply the right hand side by P minus transpose or something?
P minus transpose. I didn't understand. Sorry?
Q bar transforms as an anti-chiral, right?
Q bar transforms, sorry, a little louder.
Q bar transforms as an anti-chiral spinor, right?
Anti-chiral spinor. Yeah. What we want to do is the following, right? What is the correct statement? What exactly is the statement? What exactly the statement was that C times Q bar was an anti-chiral spinor. See, P minus on C times Q bar is equal to C times Q bar. Right, that is what we checked last time. Okay, so Q bar has its, Q bar is here. Now we want to multiply with C. However, we want to multiply with C transpose. Okay, so we want to check that when we do that, taking the P plus through it, taking the P plus through it gives us the right sign. Gives us the wrong sign, and this works. So sorry. So let me say this again. So what we want to do is to take this quantity P plus, P slash, and C transpose. Okay, and we want to show that we want to check what happens when we take P plus through. Now C transpose and C are the same thing up to some sign. Not going to make any difference. Okay, so this is the same thing as taking P plus through here. Okay, through P slash times C transpose. But that, you remember, gave us a sign which was minus 1 to the power n times minus 1. Minus 1 to the power n because that's what we got when we took P plus through C. And then an extra minus sign when we take P plus through gamma. Okay, so what we get in this case is minus 1 to the power n is 2, and then an extra minus sign. Okay, so totally a minus sign, which is correct because we want it to be P minus. Sorry. Let me say it more clearly. I'm claiming we've shown that this is equal to P slash C transpose times P minus. I'm claiming we've shown this. Why is that the case? Because if minus times minus 1 to the power n was plus 1, it would remain P plus. If it was minus 1, it would become P minus. But it's minus 1, so it becomes P minus. Okay? Right. So this is really what we wanted to show, and it's true. Right? Because it's the same algebra as before. Okay, excellent. So this is consistent with this chirality business. And once again, I'll just leave it to you to check that everything else works out. This, by the way, is also now obviously consistent. It's obviously consistent because minus 1 to the power n is plus 1 rather than minus 1. Okay, so when we take this through, nothing changes. And that's consistent with the fact that this is P plus and P plus. Clear? So it's just the opposite of what happened last time. Right? Last time we had a P plus with P minus is equals C was consistent. That's because minus 1 to the power n was odd. Here we have Q plus with Q plus is equal to C is consistent. This is because minus 1 to the power n is even. Okay, so with chirality all this is consistent, and for everything else I'll leave you to check. Okay, what was the R symmetry in this case? R symmetry was UN. What about Zij? Well, Zij transforms in the adjoint of UN because it transforms like fundamental times anti-fundamental. Okay, so it transforms like fundamental times anti-fundamental of UN. If there could be a path that was delta Ij, then there could be an adjoint. I'm sorry, I said it wrong. Fundamentals, sorry, so two-index symmetric. Two-index symmetric. Oh, now whether symmetric or anti-symmetric we should check. Right, here there is a question of symmetry or anti-symmetry because these are equal type things. Okay, so that is the question of whether C. See, we know that P plus going through here is okay. So forget the P plus. It's just a question of the symmetry of C. Because P plus on this is the same as P plus, right? It's the same as that object. Yes, and in this case, C is symmetric because what? C was what? Minus 1 to the power n to n plus 1, right? By 2. C transpose was this. So the C is, n is 2. So there's 2 into 3 by 2. So I'm getting antisymmetric. And therefore Z will be antisymmetric, and let me check. Yeah, Z is antisymmetric in this dimension. In these dimensions. So C is antisymmetric, therefore Z is antisymmetric. Okay, so sorry. So Z was a 2-index antisymmetric object. Okay, and that completes our discussion of these algebras.
So this asymmetry UN, in that n is the number of chiral cycles.
Exactly. N is the number of complex chiral charges. Okay, so if there's one complex chiral charge,
That's the corresponding anti.
it's you get U1. Okay, yeah. So if there's one complex chiral charge, you get U1, and now just one minute. Yeah, right. One complex chiral charge, you get U1. Right, and the fact that Z is antisymmetric tells you that the first time that you can have non-trivial central extension is when n is equal to 2. Right, so n equals 1 theories don't have central extensions, but n equals 2 theories have central extensions. This we know again is true. Seiberg-Witten theory. No, because they're complex conjugates of each other. So we can just choose all our charges to be chiral. Then their complex conjugates are the antichirals. Suppose you started with 3 chirals and 2 antichirals. Let me deal with the complex conjugate of your antichirals. So that's 5 chirals. So that's what we have.
The total charges will be 10.
Total charges will be 10 depending on how you count. You see, these are, you may want to count real supercharges. But if you, the way you said it, in this case 3 chiral, 2 antichiral, which is now same as 5 chiral, I would say n is equal to 5. Okay, now how many real supercharges do you have? You will have 20 real supercharges. Why is that? Okay, you see, every supercharge is a chiral spinor that has 2 components, but it's complex, so it's 4 real components. So the total number of real supercharges is what I'm calling n times 4. I mean, I'm working in 4 dimensions. For 8 you have to do a separate count. Right? You have to count the number of components in a real complex, a chiral complex supercharge, if you want the number of real components. But we're classifying it by number of chiral spinors, complex chiral spinors, that's n. Is this clear? Okay. Okay, so I think we're done. Any questions or comments? I'm sorry I've gone so slow. And thank you for helping me out with algebra, all you people. Thank you, Kanu and Chintan and Sunil and Rakshu and everyone. And of course, Shuman.
What was that comment of multiplied by 4 kg?
Okay. What we're doing is counting how many chiral complex spinors we have. Now there are 2 cases we're dealing with, or many cases we're dealing, 4, 8, so on. The number I'm going to multiply by will depend on the dimension. Let me say I'm working with d equals 4. For the comment that I made, I was working in d equals 4. Okay? How many components do we have? How many components do we have in a chiral spinor in d equals 4? Chiral spinor, so 2. Right? But each of these is complex. So the number of real fields in that is 4. So if I say that I'm dealing with a theory classified by n, the total number of real supercharges is 4n. Okay? So this will have as much supersymmetry as n equals 1 in 4 dimensions. We'll have as many real supercharges as 4 real supercharges in the quantum mechanics we dealt with in the beginning of the lectures. As many supercharges. Okay. Any other questions or comments about this?
So there is a comment that when the Q transforms as the Uij, that Zij will not be there.
Can't hear you. When Q transforms as Uij, what do you mean? Oh, you mean when you do the R symmetry transform?
Then Zij won't be there.
No, can be there. It's just that Z also transforms. Right? So in this case, for instance, Z transforms like the 2-index antisymmetric tensor of Un. Is this clear? Yeah. Okay. So, yeah, right. No, it can be there and yeah.
Doesn't stay invariant.
Doesn't stay invariant. That's the point that we extended the algebra.
Oh, those are the charges you're saying.
Yeah, we extended the algebra, and the algebra had non-trivial commutators between generators of R symmetry and Q, and generators of R symmetry and Z. Okay?
So when you counted this one, like,
Yes.
when you counted like 4 times that thing, that is like Majorana function, right? In some sense.
I'm counting number of real components, number of real numbers you need to specify the spinor.
So antichiral is just conjugate of.
See, I'm taking a chiral, right, exactly. The antichiral is the conjugate. There's no new information in the antichiral. Yeah. Exactly. Yes?
Zij does not stay invariant. The commutator also does not stay invariant, right?
Under U? Well, Z itself is a charge. Okay? If you have the commutator of something, it has to, both sides have to transform the same way under Un, under the R symmetry. But they do. Right? Because the left hand side Q is transformed, on the right hand side Z is transformed. Delta Ij was special because it was an invariant. So you could build it out of numbers. Okay? Here, there's no invariant built out of numbers that transforms in some, I don't know, with the right symmetry properties. So you need a new charge. But there is a new charge in your theory. Those are Zij's. And they have the properties that they commute with everything in the algebra except Un. Okay? And that they transform the right way under Un. So that's okay. Okay? Other questions, comments?
So in the case of odd dimensions, when dimension is 1, 9,
Yes.
so there the commutator has peaks both delta and Z.
Yes.
So one is like invariant under SON and other is other transforms like so.
Yes. That's fine, because you see delta was invariant by itself. Therefore, it could be a number. You see, what's the point? As Kanu says, left and right hand side have to transform in the same way under SON. Okay? Left hand side has charges, they're transforming. In the case of delta, right hand side doesn't have charges, it's just a number. Number doesn't transform, right? Commutator of a number with any charge is 0. So it had better be true that the transformation of the left hand side just left that number invariant. But that's true of delta Ij. It's not true of some arbitrary, let's say, I can't remember whether it's symmetric or antisymmetric, but an arbitrary tensor. But that's not a problem, because now in that case, the tensors are not numbers, they're charges. They have independent transformation properties under this. Clear, Sakshu?
So when you are transforming Qi, you have to specify what J transforms as.
Exactly.
Is that given at the same time?
It's given at the same time, and we figure it out. Right? It clearly was some representation in the product of I and J. But that could have been either symmetric or antisymmetric. Which one is figured? we've figured out in each case. Clear? Any other questions? Okay. Any other question? Okay, excellent. So that we're done. I'm sorry for going over time. I'll try to avoid this in the future. So now you have your first brush with the supersymmetry algebras. In the next class, we will examine representations of these algebras. Okay, what we will do is the following. Are all of you familiar with the little group analysis of particle content of theories with the Lorentz algebra? Anyone not familiar with that? So if someone is not familiar, you should tell me, because then I'll review it. And then we will repeat the same thing with supersymmetry. Okay? So we will try to find out how particles or groups of particles transform, appear in representations of this algebra, which will give us a lot of information already about the theory. After we do that, we will continue to discussing superconformal algebras. So we'll have 3 or 4 lectures maybe on superconformal algebras and their representation theory. And then we will turn to a study of actual theories. We'll study 2-dimensional theories of these gauge linear sigma models. This beautiful paper by Witten on that. We'll study Seiberg duality and Seiberg-Witten theory. That's 2 dimensions, 4 dimensions, and then we'll do something in 3 dimensions. I'm not yet sure what. Maybe A maximization, that Z maximization. And we'll study something in 5 dimensions, something in 6 dimensions, just to get a flavor for dynamics of all these dimensions. Okay, that's it.